Welcome to the ASP benchmark generator tutorial. In this video, I will present how to install the program, create an instance of a configuration problem, generate its ASP encoding, and obtain the solutions in a form of answer sets. To install the program, navigate to its GitHub page, then clone the repository or download it as a zip, which is what I will do now. Extract the downloaded file. Next, open the Anaconda prompt and change the directory to the one containing extracted downloaded files. Then simply follow the instructions from the GitHub page. Copy and paste the commands into the prompt and execute them. First, create a new Conda environment from file. This can sometimes take a moment. Next, activate the newly created environment. Finally, execute the main script. The program should be working. Once we have the program running, let's create an instance of the configuration problem. The subject of the configuration will be a PC to play games on. The information will be made up and not entirely accurate, but it should only serve the purpose of presenting the program's usage. Let's define some general requirements. We assume that a valid PC has one motherboard, one power supply unit, one processor, between 1 and 2 graphic cards, between 1 and 4 RAM units, between 1 and 6 disk drives, one operating system, and an arbitrary number of games. Next, we will define the taxonomy of available computer components. They fall into two disjoint categories: devices and software. In the software category, we can distinguish between operating system and games, whereas in the device category, there are motherboards, processors, graphic cards, power supply units, RAM units, and disk drives. The subcategories can further divide into more specific subcategories, and eventually into concrete elements. Computer software can only be installed provided that there is enough disk space. Let us now define the capacity of the disk drives and space required by the software. The balance must eventually be greater or equal than 0. Another aspect is part compatibility. To present the concept of ports and its compatibility, let's assume that the motherboard are only compatible with GPUs of a specific brand. We assume that the MSI Ace motherboard has 2 GPU ports compatible with NVIDIA GPUs only. MSI Tomahawk has 2 GPU ports too, compatible with both NVIDIA and AMD. And Asus Prime has only 1 GPU port, compatible only with AMD GPUs. To show how to express additional constraints, let's impose some additional restrictions. Constraint 1. We want the game FIFA installed on our PC. Constraint 2. We want between 3 and 4 distinct RAM units. Constraint 3. The games FIFA, Tekken, and GTA are only compatible with Windows. Constraint 4. We assume that having 3 or more RAM units is so energy consuming that we either need a powerful power supply unit or a very low performance and energy saving processor. Okay, let's try to formalize that using the program. We choose to create new project. As the name of the root component, we type PC. First of all, we should define the taxonomy of component types. I will continue to call them just components. To add a component, we can use add sibling or add child options. Since the taxonomy doesn't contain any element yet, it does not matter which option we choose to add the first component. Let's call this first component component 1. We will add its sibling and call it component 2. Now let's add some subcomponents. Select component 1 and click add child to add a subcomponent child A. Now add child B as a sibling of child A. We will also add a child of component 2, child C, and its child, child D. Okay, now if we want to rename any component, we simply select it, then pick rename and input its new name. To remove a component, select it and click remove. It is also possible to remove an element and all its offspring. To do that, select the component and click remove recursively. If you select a component that has children and simply remove it, its children will not be removed. Instead, they will take place in the hierarchy of the removed parent. But adding components one by one this way would be really tiresome. These options are intended to edit existing taxonomy. Instead, when creating a taxonomy, select Create Taxonomy. Then input all the components one by one in each line. If a component is on the same indentation level as a component above, then these two are siblings. If, however, a component's name is preceded by a tab, then it's a child of the first component above that does not have the tab. That's how we can easily obtain the same result. Okay, now let's create the actual taxonomy of the PC components. By simply pasting previously prepared text, we can create the taxonomy very quickly. Let's check it. Now let's switch to the Associations tab. Here we can specify how many components of a certain type are required. To add an association, select a component this association concerns. Then tick the Has Association checkbox. Now to add a lower bound, tick the Has Min checkbox and input it below. Add the upper bound in the same way. Because we require that a PC has exactly one motherboard, we set both bounds to 1. Next, we will do the same for the CPU. We set both bounds to 1, because we require exactly one CPU. We require between 1 and 2 graphic cards, exactly one PSU, between 1 and 4 RAM units, between 1 and 6 disk drives, exactly one operating system, and arbitrary amount of games. Thus we can add 0 as the lower bound and not add the upper bound. Now if we make a mistake, we can remove the upper bound by unticking the has max checkbox. Lower bound by unticking the has min checkbox. We can also remove the association entirely by unticking the has association checkbox. Okay, now let us turn to ports, which is how we can add information about components compatibility. To add a port, select Add and input the port's name. To rename it, select it from the combo box, then click Rename. To assign a port to a component, ensure the port is selected from the combo box. Then select the component and input the desired amount of port instances the component should have. You can also assign the ports to all leaf children of some parent component by selecting the parent component, inputting the amount, and pressing Apply to all children. Finally, to remove the selected port, click Remove. Okay, now let us add the motherboard and the GPU ports. We create a port type that the NVIDIA graphic cards will have. Then we create a port type that all AMD graphic cards will have. Now we select the NVIDIA port type and we assign one port of that type to each NVIDIA GPU. We do the same with AMD port and AMD GPUs. Okay, now we add the GPU port types of motherboards. First, MSI ACE GPU port, then MSI Tomahawk GPU port, and finally Asus Prime GPU port. In the assumption that MSI has 2 GPU ports, MSI Tomahawk has 2 GPU ports, and Asus Prime has 1 GPU port. Now we have to set the compatibility of the ports. We select the MSI ACE GPU port and click Edit Compatibility. Here we select all port types from the list box on the left hand side that are compatible with the MSI ACE GPU port and add them to the right list box. We previously assumed that this motherboard is only compatible with NVIDIA GPUs. Now we do the same with the MSI Tomahawk GPU port. We assumed that it is compatible with both NVIDIA and AMD GPUs. Finally, we do this with the Asus Prime motherboard too. It is worth noting that because the compatibility relation is symmetric, since MSI Tomahawk and Asus Prime are both compatible with AMD GPU, then AMD GPU is also compatible with both MSI Tomahawk and Asus Prime, and the same holds for NVIDIA GPU, so we don't have to set the compatibility twice. One last thing regarding ports is forcing connection. In some cases, a component can only be a part of configuration if its port is connected. This is the case here. A GPU is not useful if it is not connected. That's why we force connection of some ports by ticking the Force Connection checkbox. We do it for ports on the GPUs, both NVIDIA and AMD. We do not force connections on the motherboard ports. Some motherboards have 2 GPU ports and we do not require them both to be connected to some GPUs. Now we move to the Resources tab. To add a resource, press Add and input resource name. To rename or remove it, make sure it is selected from the combo box above and click the Rename or Remove button respectively. We will add disk space as resource according to the assumptions. Now, to specify the component's production rate, make sure the resource is selected Then select the component and input the production amount. To set the consumption rate, simply input a negative number. It is also possible to in bulk set the consumption or production rate by selecting parent component, entering the value, and then pressing Apply to all children. We will now set the remaining values. It is possible to impose additional constraints. To do so, navigate to the Constraints tab and select Add Simple Constraint. A simple constraint is similar to an association, but gives more possibilities. Select components that should appear in the constraint from the left-hand side. We select the game FIFA 20, since this is something we enforced earlier. In the name field, input the name of the constraint. Below, you can find the description field. Filling it is optional, but it can be useful later to remember what the constraint was meant to mean. The distinct checkbox will be discussed later. Since we want to enforce that the game appears in the configuration, we set the lower bound to 1. That's all for this constraint. The second constraint enforced that we have between 3 and 4 different RAM units. We could just add the RAM component to the selected components list box and set the bounds to 3 and 4 respectively, but that would not guarantee that we have RAM units of different type. We should thus select all the different RAM types. There is an easy way of doing it. Select the parent component, RAM, and then click Add recursively. Input the name. Input the optional description. Set the lower bound to 3 and upper to 4. Now, since we need the RAM units to be different, we tick the distinct checkbox. One last thing. Adding component recursively added the parent and all its offspring. We should thus remove the RAM component from the list of selected components. Okay, the next constraint states that certain games are only compatible with Windows. This is where we will use the complex conditional constraint. Similarly to simple constraint window, we fill the name and optionally the description. Now we have these two list boxes called condition and consequence. Complex constraint enforces that whenever the condition is fulfilled, then the consequence must be fulfilled too. Our constraint is of the form of the condition as well. We can formulate it as if there is a game of FIFA, Tekken or GTA installed, then the operating system must be Windows. Let's add the condition. We select Add under the condition list box, and the well-known simple constraint window appears. We will use it to formalize the part of the condition. We select the games Tekken 7, GTA 5 and FIFA 20. Input the name and input the lower bound of 1, because an appearance of any of those will be sufficient to activate the implication. Okay, Now that the condition is formalized, we can formalize the consequent. We select Add under the consequence list box, and we express that a Windows operating system is installed. Now a condition as well as consequence may have many parts. These parts can be connected by either conjunction or disjunction. If the first is required, select the All option in the radio button under list boxes. Otherwise, select any. These parts can also be edited or removed, simply by selecting them and clicking Edit or Remove respectively. Okay, let's add the last constraint. I will simply name it complex constraint and explain it in detail in the description since it's rather complicated. We want to enforce that if there is 3 or more RAM units, then either we have a powerful PSU of 750 watts or we have one of the 2 low efficiency CPUs. Okay, let's add the condition. It should be triggered if there is at least 3 RAM units. We simply select RAM since we do not care about the specific RAM type. We input the name and description. Leave the distinct checkbox unticked and set the lower bound to 3. Okay, now we add the consequence, either powerful PSU or energy-saving CPU. Let's start with the first part. Select the powerful PSU, set the lower bound to 1, enter name, now the second part. We select Intel Celeron, and Intel i3, set the lower bound to 1, and enter the name. Since we only need that either we have the energy-saving CPU or a powerful PSU, we should select any from the radio buttons below. As previously, constraints can be edited or removed by selecting them and pressing the Edit or Remove buttons respectively. Okay, the encoding is complete. But what it does not tell us is how many components of each type we actually have at our disposal. To set that, navigate to the Instances tab. To set the amount of components of a specific type, select the component type, then input the amount in the count field. In many cases, it is impossible to know the exact number, but a range is known. Then we could tick the range radio button and insert the lower and upper bound. There is also a crucial symmetry breaking option that needs to be at least briefly explained. To put it in simple words, this option restricts the number of possible answer sets by eliminating redundancy. It ensures that a combination of some cardinality is always represented by the same set. I will use an example here. Assume we have 10 elements of type A. This can be expressed by the following fact. Now assume a valid solution requires 2 of the components to be present in a configuration. The number of possible subsets is 10 choose 2, so 45. If, however, the symmetry breaking option is selected, the subset will always be represented simply by this one subset. Thus, the number of subsets is reduced from 45 to just 1. Now, if you consider that there are many different components, setting the symmetry breaking option might prevent from explosion of redundant answer sets. To set this option, simply tick the symmetry breaking checkbox. The number of all leaf children components can be set by selecting their parent component, entering number, and pressing Apply to all children. The same applies to the symmetry breaking. Symmetry breaking can also be set once and for every single component by setting the topmost checkbox and then pressing Apply button next to it. Okay, now to keep things simple, we will set the number of every device component to 10 and the number of every software component to 1. The project is complete. We can now continue to the Run menu. If one wants to generate the ASP encoding only, they should select the Generate option. If, however, one wants to solve the previously generated ASP encoding to obtain the answer sets, they should select the Solve option. To do both at the same time, select Generate and Solve, which is what I will do. On the top, we can see a list of checkboxes. They are directly translated into the show directives of the ASP program. If we wanted to show all predicates, we can tick the Show All Predicates checkbox, which will not generate any show directives and thus show all the predicates. Next, we will set the directory and the name of the generated ASP encoding. The next part concerns solving. Here we can set how many answer sets we want. We will leave the default number 1 for now. Next we can set the instance representation. As an example, the ID option only preserves ID. Textual option preserves information about the type of component, and mixed preserves them both. Next, we can set if we only want to extract the predicates that are listed in the show directives, or all of them. We will keep only those two. Finally, we can set the directory and the name of the generated CSV file with answer sets. When everything's set, select OK to start generation and solving. Let's first see the contents of the generated ASP encoding. It starts with the definition of the root component. Next, we can see the rule that there can only be one root component in a configuration, followed by the taxonomy of components. Next, we have general rules, or so-called ontology definitions, regarding associations, followed by the associations themselves. For example, that there has to be only one CPU or between 1 and 6 disk drives. Then we have a rule stating that resource balance must be greater than or equal 0, and information about components, resource production and consumption. After that, there is port information. For example, that the ports of AMD Sapphire GPU and Asus Prime motherboard are compatible with each other. Then we can see the FIFA installed constraint, the at least 3 different RAM unit types constraint, the compatibility of some games with the Windows operating system, and the complex constraints. After that, there is instances information. After that, there are the show directives. Now let us turn to the answer set file. I will quickly make the file a bit more readable. Let's check whether the solution satisfies all the imposed restrictions. We will start off with the association. We have exactly one root element, the PC itself, exactly one motherboard, exactly one CPU, one GPU, which is between 1 and 2, exactly one PSU, 4 RAM units, which is between 1 and 4, one disk drive, which is between 1 and 6, exactly one operating system, and one game, which is between 0 and infinity. The ports are listed as parts of the configuration too, so we have ASUS Prime GPU port and AMD Sapphire Radeon GPU port. Another restriction we imposed was compatibility. We said that ASUS Prime motherboard is only compatible with AMD GPU, so we have an ASUS Prime motherboard and an AMD GPU, and they are connected as indicated by the CN predicate. Okay, now let's check the disk space balance. Windows 10 consumes 40 GB and FIFA 20 50 GB. So 90 GB of disk space is occupied, which is greater than 2 TB produced by the disk drive. Finally, let's check the constraints. First of all, FIFA is installed as required. We also required between 3 and 4 RAM units, and as we can see, this constraint is satisfied since we have 4 RAM units of different types. Third constraint stated that FIFA and other games are only compatible with Windows OS. Finally, if we have 3 or more RAM units, then we either should have a 750 watts power supply or a low efficiency CPU. We can see that we don't have a low efficiency CPU, but what we do have is the powerful power supply. As we can see, the solution is correct. What is also worth showing is enumeration of all answer sets. To do so, input 0 in the answer sets count field. You can stop the generation at any point and still preserve all so far generated answer sets. To change the name of the root component, select Edit, then Change root name. To save the project, select File and then Save. A more comprehensive user guide can be found on the GitHub page or in the Help menu. When the project is launched again, the recently closed project can be quickly opened from the list box on the left or upon clicking the Open button. Also, once we have generated the ASP encoding, we can quickly solve it using the Solve option. This concludes the tutorial. In case of any problems, please refer to the GitHub page or send me an email. But I hope there won't be many though. Thanks for watching and goodbye.